Excellent. And you can see my slide. Okay. So can I start?
Yes, please.
Okay, excellent. So thanks a lot to everyone who was involved in putting together this conference and for the opportunity to speak here. So the subject is test measure Renyi divergences. This is joint work with Fumio Hiai, and you can see the paper on the archive. Okay, so let me start with some basic definitions first. As you all know, for two probability distributions on a finite set, this is how their Renyi alpha divergences are defined. And from this, we can define various quantum extensions. Today, I'm going to be mainly interested in the measured Renyi divergences, which are just taking arbitrary finite outcome measurements, looking at the classical Renyi alpha divergence of the post-measurement probability distributions and optimizing overall possible measurements. Okay, and I will be interested in a variant of this when we only allow two outcome measurements, also called tests. And this is very natural to consider in a binary state discrimination problem when we apply two outcome measurements. So these are the post-measurement Renyi divergences after a test in a binary state discrimination problem. And it's also very common to consider regularizations of these quantities. So the regularized measured Renyi divergence is a very well-studied quantity. Here is the definition. And here we have the equality of the supremum and the limit, because as is also very well known, if you take two POVMs on different system sizes, then we can construct the tensor product POVM on the composite system. But if we had M1 and M2 outcomes for the two measurements, then of course the product has M1 times M2 measurements. So in particular for tests, the product is not going to be a test. So for this reason, when we are interested in the test measured Renyi divergences, there is no easy way to see whether these test measured Renyi divergences are super additive, or whether these two quantities, so the supremum and the limit, I put lim sup here just to be safe, are equal. And in fact, there is no difficult way to see it either, because neither of this is true, at least for alpha smaller than 1. So I will show this. Okay. Here are a few simple or well-known relations between these quantities. So the inequalities in the upper two lines are obvious from definition, right? So here we consider less measurements than here. This is a lim sup, this is a supremum. And here again, we consider more measurements than here. Okay. It is also well known that these regularized measured Renyi divergences can be expressed as the sandwich Renyi divergences for alpha between 1/2 and plus infinity, and the different family of alpha Z Renyi divergences for alpha between 0 and 1/2. Okay. And they are upper bounded by the pastime quantum Renyi divergence. Right. It is also quite easy to see that all these red quantities, so all the measured quantities, are the same as the PES type for commuting states. And it is less easy, but still true, that all the regularized quantities are the same for alpha larger than 1. Okay, and one can see this by taking an optimal test sequence for the strong converge exponent of asymptotic IID binary state discrimination. And that optimal test sequence will make these quantities equal. Right. It's probably important to note that this is not at all obvious that this is possible, because in order to attain this measured relative entropy, measured Renyi divergence for finite number of copies, it generally requires a number of measurement outcomes that diverges in n. So it goes to plus infinity. So it's a bit surprising that in the limit, considering only two measurements is sufficient. Okay, and what I will show is that none of these inequalities are equalities when alpha is smaller than 1, unlike for the alpha larger than 1 case. Okay, so before I explain that, let us have a quick look at various operational interpretations of these quantities. So in the setting of binary state discrimination, where we are testing n copies of rho against n copies of sigma, it is common to define this optimal type 1 error probability under the constraint that the optimal type 2 probability is below this exponential factor. And it is well known that in the asymptotic limit, 1 minus these quantities go to 0 exponentially when R is large. And this exponent can be expressed by the so-called Höfding antidivergence, which is a certain transform of all the regularized test measured Renyi divergences. So I could write regularized measured here, or I could also write the sandwich Renyi divergences here because they're all the same, but here I want to emphasize the role of this quantity. Okay, and for alpha larger than 1, we have an analogous operational interpretation. This is called the Höfding bounds theorem. So here this error probability goes to 0 exponentially, and the exponent can be expressed by this formula. This transform of the PETS type Renyi divergences is called the Höfding divergence, and we are going to use it in the following slides. So these are two operational interpretations for these two quantum Renyi divergences. They are not direct operational interpretations, but certain transforms of these quantities. And one can get direct operational interpretations by considering the so-called generalized cutoff rates introduced by Chisar. I'm not going to explain it because it's not really relevant for us what it exactly is, but it exists. And analogously, I didn't write it for the alpha smaller than 1 case, but also there we can get such a direct operational interpretation. But this is not actually what I'm interested in here, but rather a different operational interpretation for a different family of quantities, where we are considering this expression. So we have the type 2 error probability and the type 1 error probability. And the idea is that we want to make their exponents equal. And we achieve that by introducing an additive constant on the level of exponents. Okay, so this minus c is an additive constant. And if you optimize this and look at the exponential decay rate, then this can be expressed in terms of the PETS type Renyi divergences by this variational formula. Okay, and now instead of introducing an additive correction for the error exponents, we can introduce a multiplicative correction, right? And if you choose this multiplicative correction in the right way, in this case it's alpha over 1 minus alpha, then it turns out that the exponent of this quantity is exactly this regularized test measured Renyi divergence, alpha Renyi divergence. Okay, so these quantities have a direct operation interpretation, unlike the other quantities. I mean, we have direct operation interpretation here, but it's much more convoluted, and it's not so obvious that this is a very natural quantity to study. Here, this is much cleaner, much nicer. Okay, and either using the original definition or this representation, one can show this expression for these regularized test measured Renyi divergences. So actually, this hypothesis testing problem has been considered before by Zalcman and Datta in a paper before ours, and they also came up with this expression. And in the non-pathological case, this simply means that in order to get this regularized test measured Renyi divergence, we need to look at the curve of the Höfding divergences, which looks like this as a function of R for fixed rho and sigma. And we just draw a straight line from the origin with slope 1 minus alpha over alpha. And the intersection of this straight line with the Höfding divergence curve gives us the regularized test measured Renyi divergence as the x coordinate of this intersection. Okay, so this is the geometric meaning of this representation. Now, this is computationally not very simple because each of these HRs include an optimization already over all the alphas between 0 and 1. And Zalcman and Datta show a different representation, which is much nicer from the computational point of view, which looks like this, because it works directly with the Renyi divergences. Okay, so these are not explicit formulas, and probably we can't even hope for any explicit formulas. but at least they are single copy, right? And it's not at all obvious a priori that we should have a single copy expression for these quantities. And just a remark that all this work in the most general von Neumann algebra setting, not only in finite dimension. Okay, so let's see what we get from these representations. So this was the expression that we obtained for these quantities. And it is clear that these regularized divergences are upper bounded by the best type, simply because of monotonicity of the best type Renyi divergences. And from this, we also get a lower bound. So they cannot be smaller than 1/2 times the best type Renyi divergences. And what we are interested in is when this equality is saturated. And it turns out that it is almost always a strict inequality. So if we have the spectral decompositions of the two states, then the following is true, that we have equality here for some alpha, if and only if we have it for every alpha, if and only if we not only have it for every alpha, but also for every finite size n. And this can happen if and only if rho and sigma are in a very special relation. So either all the spectral projections of rho are sub-projections of the spectral projections of sigma, and all the eigenvalues of rho are a fixed constant multiple of the eigenvalues of sigma, or the other way around. Right, so this is really, really very, very special. In particular, they have to commute with each other. Okay, and because this is hardly ever satisfied, we see that in general there is a strict inequality here, and this inequality is strict even for commuting states. Okay, and this shows that in fact for commuting states, this regularized test measure Renyi divergence is not equal to the unique classical Renyi divergence. So this means that in the quantum case, this is not a quantum extension of the classical Renyi alpha divergence for any alpha. So this is in fact not a quantum Renyi alpha divergence. Okay, so this is one of the main observations. Let me show a few other consequences of this representation. So it's very easy to obtain from this that for any alpha beta between 0 and 1, we have such an inequality between the alpha and the beta Renyi divergences of rho and sigma. This is trivial when alpha is larger than beta. It's actually worse than what we get from monotonicity. But when alpha is smaller than beta, then this is a non-trivial inequality. I have to admit that I have no idea if it is good for anything. I'm not aware of similar inequalities with multiplicative constants, but if anyone knows such inequalities, I would be very happy to know about them. And I also mentioned that unfortunately, this doesn't give us an inequality between Renyi alpha divergences and the relative entropy, because when we go with beta to 1, then this becomes 0 and this whole inequality becomes trivial. Okay, and another corollary that we can get from this representation is that even though these quantities are different from the best type Renyi divergences, in the two endpoints at 0 and 1, they actually coincide with the corresponding limits of the best type Renyi divergences, so the 0 Renyi divergence and the omega relative entropy. And for alpha equals 1/2, we get the Chernoff divergence. Okay, so this might be interesting too. Right, so we have established that one kind of regularization of the test measure Renyi divergences is strictly smaller than the alpha, even for commuting states. And now the question is, what about the other one? So this is, in principle, it can be larger than this lim-sup definition. So it could happen that, say, for commuting states, we can achieve this quantity. And it's, of course, a related question whether these two definitions are the same or not. And it will turn out that they can be different, and here we can have strict inequality. Okay, so as a preparation for this, so we have already shown that this lim-sup is strictly smaller than d alpha. And of course, it is not enough to conclude that the supremum is strictly smaller, because in general, the lim-sup is smaller than the supremum, so or cannot be larger. And in general, also, if every element of a sequence is strictly smaller than a number, then this also does not imply that the supremum is strictly smaller than this number. But interestingly, combining these two insufficient conditions, we get a sufficient condition. And this is very easy to see. So we have already established this strict inequality for generic state pairs. So now we are going to focus on finite size relations. Okay, and for that, we have this chain of inequalities. So again, obviously the test measured is dominated by the measured, which is dominated by the regularized measured. And for alpha equals 1/2, we choose the Betz type here, and these are dominated by the best type Renyi divergences. And we are interested in comparing the two endpoints of these inequalities. But we can see that already to have equality here in the middle, rho and sigma have to commute with each other, right? So we can have equality here for some alpha if and only if we have equality for every alpha, sorry, maybe this is not if and only. Yeah, that it is. And these imply that rho and sigma have to commute with each other, right? So we have some support constraints here. These have already been considered by Berta Fauzi and Thomas Michel under different support conditions, and yeah, this is just a variant of it. Okay, so the point is that if you want to have equalities between the two endpoints, then we have to consider commuting states. So this is the last thing I'm going to show. So consider two commuting density operators, and for simplicity, we assume that they have the same support. Then it's quite easy to show that the following statements are equivalent, that these differently regularized, so the supremum regularized test measure Renyi divergence is the same as well, the unique classical Renyi divergence, either for every alpha or for some alpha. These are again equivalent. And this can happen if and only if already for a single copy we have this equivalence, this equality. And again, this can only happen in a very special case, if and only if this set omega on which this probability distributions live can be divided into two disjoint parts, such that on both of these sets, rho is a constant multiple of sigma. And these constants can, of course, be different from each other. Okay, so this is again very, very special for commuting states. And if this is not satisfied, then again, this supremum regularized test measure Renyi divergence is strictly smaller than the unique classical Renyi divergence. So again, this version of the regularized test measure Renyi divergence is not a quantum extension of the classical Renyi divergences. Okay, and as it was kindly pointed out by a referee to us, which we haven't noticed first, that if we have such a state, then we have equality here. But if the C0 is not equal to C1, so basically if rho is not equal to sigma, then we have a strict inequality between the two types of regularizations, right? So these two things are not equal to each other. Okay, so this is all I wanted to say. Thanks a lot for your attention.
Thank you very much. And thanks to you, we're back on time. Anyone has questions? Well, maybe when people are thinking, I have a small question. Maybe I missed this. So when you regularize the measure, the number of measurement values can grow with n, right?
Mm-hmm. Yeah.
So if you say I want this number of measures to be fixed, not grow with n, but it can be more than 2, does that give you some full quantity? So you can have more than.
Yeah, that's quite a natural question to ask. I'm not sure what you get if you fix. I would imagine that you don't get back the sandwich Renyi divergence. But I don't know what exactly you will get.
Okay, thanks. Do other people have questions?
sorry, I have one comment. So, in your talk, I was saying that so this alpha has some no. This Renyi divergence has some complicated behavior only when alpha belongs to zero. Alpha belongs to between the 0 and 1.
Yeah.
So if alpha is greater than 1, so in that case, this divergence is same as test divergence same as that quantum.
Right, sorry, for alpha larger than 1 is same as the sandwich to any divergence.
Sandwich also, then the behavior is much more natural. So this is somehow related to the proof method. In the case of strong converse, essentially we use that kind of some information processing inequality only with the two outcomes. So that kind of bound also will be achieved by using the hypothesis testing. So in this sense, we can easily find that the test divergence equal to the sandwich divergence. But in the case of holding bound, in that case, the situation is very complicated. So at least we don't consider that kind of converse proof. The converse proof uses a much different method. So this is somehow the reason why you have that more complicated behavior in the case of test divergence.
Probably, yeah.
Usually, when we discuss the how to say converse part of holding lemma, we never consider two outcome linear entropy. Instead of this, usually we discuss how to say that one. We discuss we discuss that one. I cannot remember. Cramer theory. So
yeah, sure.
So the idea is completely different. So in order to understand why we do not discuss that kind of method, maybe in that behind there is a very complicated behavior. Now you explain, but usually we don't need to discuss that complicated issue. We only focus on the hypothesis testing. This is very complicated behavior.
Okay, thank you.
There is one.
Yeah, there are two questions. I think maybe Mark first.
Hi, Milan. Thanks for your talk. Can you go to the slide with Chernoff information? I forget where that was. It seems like it was midway.
Yeah, here. Yeah.
Yeah. So this is very interesting. Oh, you need regularized. Okay. So we know that the measured Renyi relative entropy of order 1/2 gives you fidelity, right?
Yeah.
But the test version at 1/2, I guess, including regularization, gives you Chernoff. That seems very interesting. Can you comment more about that?
Not sure. So, well, I mean, the fact that you get this, okay, so you have this expression, and this is a formal thing, and you can get that this is equal to the Chernoff, but you also have this operational interpretation, and this was considered by Zaltzman and Datta before. So if alpha is 1/2, this is just 1, right? And you just get the Chernoff problem. Yeah. So maybe that's one component. And yeah.
The other question I had is at the other end of this is the max relative entropy when alpha is infinity.
Yeah.
I can't remember in your talk if you commented about that. Is the max relative entropy achievable by a test?
Oh, yes. By a 2 outcome test, yeah.
Okay, and that was in your 2013 paper, right, at the very end?
I don't know, but maybe.
Okay.
But it's
Ogawa.
it's very easy to see actually.
Okay. Thanks.
Okay, thanks for the question.
Thanks. There's another question. Ajit, do you want to ask on the microphone, or shall I read it? So maybe I'll read the question, which is written here. For commuting, will you not go right at the beginning to common diagonalization and classical case?
Yeah.
Yeah, so I guess it's
Yes.
more like the if only if part that.
So that's what we do. So yeah, in the commuting case, we consider jointly diagonalized states.
Yes.
I don't know if this was the question or.
Yeah,
or
I don't know either. Sounds like it's satisfied.
Okay.
If not, please complain.
Glad to hear that.
Okay, so okay, thank you very much again.
Thanks a lot again.
To all the speakers, all three speakers of the session, and the audience as well, of course. So
okay, thank you.
Of that physically.